Hello again.
Hello.
It's been a long time, but we're back. We're going to try something different, and we're going to try Advent of Code is what we're going to try and go through some of the issues, problems, and see if it's interesting that we've both been working on them and doing something different.
So yours are in KDB or Q? Am I saying it right? Yours are in Q in the KDB's language. Mine are in Elixir, which I don't really know. I didn't really know any Elixir until I started this, and I just used it as a way to learn. But I think I'm doing okay. So we'll see.
So Advent of Code, if you haven't heard about it, how would you describe it?
It's a daily Advent calendar, so from 1 to 25, running in the run-up to Christmas, and it's a challenge every day. They explain the problem, and then you write a program in any which way you want. One of the guys that were in my office solved the first one in Excel is a formula, which is a pretty good effort. And then it gives you an answer, and that answer is usually a number, but sometimes a string. And then you paste that into the site, and it goes, yep, you got it right, or no, you didn't get it right. And then there's 2 parts to each day. So it's normally a question and then an extension to that question. And some days lead on from one another. So
the Intcode computer, which we might get to, will be one of those.
So 4 of the days have basically been the same problem, which has been extended 3 times, and I hope I never see it again at this point.
I think it's going to make a comeback.
I hope not. It says it's like the final thing. Oh God, I hope not. If it does come back, I need to write unit tests. I decided yesterday because it's getting that silly. Yeah. But should we have a look at number 1? We'll put a link to this, and you can, if you want to read it all, you can read it all.
Yeah, it might be easier. Yeah, if you want to sort of play along, you could have a read of it, and then we can talk about it.
I barely remember what this one was about, actually.
No,
it's not. It's the first day, so it's a bit of a sitter.
Yeah. So module and mass, and then you've got to calculate for a set of modules what's the total sum of the fuel requirements based on this equation in this paragraph,
which was divide by 3, round down, then subtract 2 by the looks of it.
Yeah. Cool. And then they have some examples here, and then we need to input some values. I'm not signed in here, so you can't see what I did. But I guess the question is here, is there any interesting way to solve this one? Maybe there isn't, but it's quite simple. But how did you do it?
I can't remember. How did I do it? So the program starts on line 9. What you're going to see, I've just realised from looking at this, is an evolution of me learning how to do things better in Elixir, because I'm already looking at this code thinking, what are you doing? But I read the file, split it to get the numbers, and then I pass those as integers, and that's all pretty horrendous up until 11. So that's just getting the numbers. And then for each mass, I map over them, calculate how much fuel's needed, and then
And this fuel for mass here is a function, isn't it?
Line 12 is just not even needed. So it maps over them, calculates the fuel, and then just sums them. So Elixir has a lot of library functions to do like higher order things.
Yeah.
And then I've done
like the enum.sum, for example, I assume.
Yeah, so it has a floor division function, which I used, and then -2. And that's it. So it was pretty straightforward.
Yeah, so I guess the key here is that you've got to do this calculation over every element.
Did I put an example in there or no? No, I've not even put an example. I've not even done these ones. The examples.
I normally run through them with the examples, but
shall we see the KDB?
Yeah.
Or the Q. What is the technical? Don't let me sound like an idiot.
It is Q.
Oh dear Lord. Okay, well.
So so my syntax generally is that the first day is day and then P.
So it's kind of like names.
So this is a namespace.
Yeah.
And then this is the function name. So in the D1 namespace, I've got a function called P1, which takes no arguments. What I'm doing in here is loading the file into the raw file data into this file data value.
So that's an assignment.
Yeah, this is an assignment.
How do you,
into the global namespace because it's in the root.
So if for those of you unaware about Q, it has a little bit of a reputation for being
hard to read,
and quite short.
Yeah, I think terse.
Yeah, what's that word they use? Idiomatic. Is it idiomatic they use to mean Q code that's like the the best practice of Q code? I think is very short.
I think what you'll find is at the start I tried to be fancy with KDB, and then as they got harder, I just need to just get the damn thing solved.
So you read it in.
So read it into this variable, and then, but this is basically doing your integer parse into the long type, which is J, and then
I'm trying not to swear, but okay. So that
so these are so all of the types have a letter. Basically.
What does dollar mean?
Cast.
Right. And why is there a dollar on line 3 as well? If you highlight that.
So this is also cast. This is casting this string into a symbol, which is what's the argument type that's needed for this read 0 function.
Okay.
The reason I've got to cast it from a symbol, from a string to a symbol, is because I've got funny characters in it.
It's a backtick symbol then.
Yeah, so you could also put this as backtick, the word backtick symbol, or you could do the backtick also means backtick symbol basically. So this is a cast. This is a parse because it's using a different value on the left hand side of the dollar basically.
Okay. Yeah, it kind of makes sense. You're casting it into. You're basically saying I've got this thing as strings and now I want it as numbers, and it's just different.
Yeah. So all the types have letters basically. So integer is I, and therefore they made long the letter after I, which is why it's J, which is a bit like I think Java has something similar. I think you do.
I've seen those I's and J's knocking about. Actually, now I think about it.
So I think it is a relatively common thing.
So are we reading this right to left? This line.
Yeah. So the other thing about KDB is that you read it right to left, which means that's why I'm using this weird syntax. So I'm trying to reduce the number of brackets I'm using. So what this is saying is this is a partial function where the second argument of divide, which is the % sign, is 3. So I'm taking all of the inputs and dividing them all by 3.
Right.
I'm then flooring them all. I'm then taking 2 away from all of them, and then I'm summing across them all.
So
it's all as a vector.
You can almost imagine that these are function calls with the brackets omitted. Is that kind of fair? So
So this literally is a function. So this I've created a function which is divide by 3. That's what that is, and then I've passed in as the first argument, because this semicolon is here. There's the first argument's not provided, and then I'm providing it after the fact.
That's really weird. So you can not provide not even the second argument. You've not provided the first argument.
Yeah, which is why the syntax.
And it just automatically operates on arrays.
Yeah, so all of the built-in, or most of the built-in operators will work the same on on atoms and lists.
Oh, you can do either.
Yeah, so
that's like R. The language R is like vectorized, and it's the same. Like you can say like something plus something. You can say a vector like 1, 2, 3 plus 1, 2, 3, and it will give you 2, 4, 6.
Yeah. KDB will behave exactly the same.
That's interesting.
So that's what. So then I'm flooring all of them, and then I'm taking 2 off all of them, and then summing. And that sum obviously gives you an atom.
I kind of get it.
Yeah, I think it's quite succinct.
And then that is got to be close to the shortest that you can do this, because you've basically done it in line 3 and 6.
I'm sure some of the other KDB experts have done it shorter than this. Right.
So we logged in. We can see the extension to this question, which was. I actually do remember.
Yeah. So the extension is that fuel itself. So in the original one, you're assuming you've got to weigh the modules, but you don't have to worry about the fuel having any weight. And in the second part, you now do have to worry about the weight.
So if you have 3 modules and you calculate that they each need 5 fuel, then you need to then say each fuel weighs 5. So how much fuel do you need for the fuel? So it's kind of, and it just keeps going. And at a certain point, you just round it down
to 0. Yeah. Once it's less than a whole number or something.
Yeah. Once it's less than 1, you just say.
Yeah. So actually your answer's here now as well, which is nice. So then you just, so you have to adjust it to say, well, what do I do? You have to include the fuel in top of the original question, right?
Let's see your solution looked. Let's see, how did you do it?
Yeah, how am I going to switch between these reliably? I don't know.
We'll do it.
So this syntax now is more awkward. So that's the fuel calculation function there.
Yes.
And what was interesting is that when I was discussing it with the other guys, I was doing full division and then flooring it, whereas obviously you could just do integer division, which also gives you just the integer value.
Yeah, I think that's what I had.
Yeah. So that's that. And then this is basically this 0 pipe is basically a cheat for max. Right. So this is saying either 0. If this goes negative, then it's just going to return 0.
Is it saying? So if this goes negative, it's just.
So this codes for if the number goes below 0.
Right.
You just you don't count negative fuel. You just count it as 0 fuel.
Yeah.
That's also important for this iteration function
And
here.
then what's 1 underscore?
So 1 is just dropping the first. So that's just dropping the first result of this output.
Yeah.
Which will make. Which I can't exactly remember why that is, but it'll be some sort of double counting.
Yeah.
This bracketed backslash is. It's like a while loop, basically. It's basically looping over this, but this is called scan, I think. So what it's going to do is it's going to take the input and then iterate over this until the output is stable, i.e. it
stops
0.
changing.
Yeah.
Wow, that's really weird.
Yeah, it is weird, and it also means if you screw it up, you can end up with an infinite loop that you can't get out of, because you obviously, like, if you have something that just flips.
Like, yeah.
Yeah. So.
And then 1 0 drops the first thing.
So that drops the first. So the point is this is showing. This also will return all of the intermediary results.
Ah, okay. So you just want the. Does it. So
what that is it's taking the initial mass, giving you the fuel, and then taking the result of what the fuel is and passing it in again.
Right.
And then it's doing that for each element in the file.
And then the calculation where it stabilizes is like the one you want to throw away, basically. Because everything's 0 twice.
Well, no, if it was 0, because we're summing it, so zeros don't matter. I think the issue here is that the first row that's returned is just the. I'd have to run it.
Maybe it's just the masses, the original masses.
So then I just want to sum everything up, and that's what this. I sum each at each. So the return of this is for each module, how much fuel is needed for the module, and then all of the fuels recursively down to 0. So then you've got a list of, for each module, the sum of everything. So then you sum each one, which is the first sum, and then the second sum is sum them all up.
Right.
So,
cool.
Self-explanatory.
Self-explanatory. That is
interesting. And then your day 2 is.
So here. I think. Okay. So I read in the file. I pass them as strings again on line 23. If you hover, then I've got line 24. It shouldn't be there, I'm pretty sure.
Yeah.
And then I map over them and sum them again.
Fuel for mass, including extra fuel.
That name in there.
Yeah, it's nice.
It's a little bit long. So for a given mass, it calculates the fuel for the mass like it did before. So that's the same function, and then it adds the fuel for the fuel.
Yeah.
For the fuel for the mass. So I could have extracted those into a variable and didn't, because they're both the same.
Fuel for mass and fuel for fuel. Okay, yeah.
So and then fuel for fuel, if it's 0, so do you want to highlight? It's on 4 through 10. So fuel for not 4 through 10, 8 through 14. So fuel for fuel is defined twice. Once if the input is 0. So this is like in Haskell when we were at uni. So if you call fuel for fuel with a parameter of 0, it will just return 0.
So you don't need to do an if statement, basically.
Yeah, it's kind of just avoiding a lift. And if you do fuel for fuel with a mass, then it does fuel for mass, which I now realise looks a lot like that function below.
Yeah, very, very similar.
It's like, if not the same, fuel for mass.
They are identical, I think.
Yeah, they are identical. So you probably could just call the top one again. I think that would probably be fine. The bottom one.
So how are you dealing with the recursion? Where am I missing?
So
is it because they're
recursion,
between fuel for fuel?
No. If you look on line 13, it's calling fuel for fuel again.
Oh yeah.
So
sorry,
it just keeps going. So
I've looked at the word fuel too much, and it now looks weird.
It does. Yeah, fuel does look weird. I had that problem the other day. And then on line 8, there's the base case. So once you get to 0,
it then fails.
But there are quite a few mistakes in this, because I could definitely eliminate a whole function there. And yeah.
So I mean, that's the other thing, right? Is that you seem to be the same. Like I'm working to just getting a result. I'm not that worried about optimization.
Yeah,
and because as well, you're learning it from scratch. It's a different game, right? So,
yeah.
So I think some of the other guys that we're doing it with are going back and optimizing once we've talked about it.
But I don't think there's no prizes for optimizing. So this is taking long enough as it is. So if we look at, maybe we should do 3 next, so we avoid the Intcodes for now. If we look at the question and maybe remember, this was crosswires.
Yeah, this was
a pain.
I remember not doing this one properly.
I think I was happy with my solution.
No, this is the one where we, as we talk about it, we did it fundamentally different ways.
Yes.
Yeah. So.
Or reasonably different. Not as different as the guy I work with, Pete. He did it really differently.
Okay, fair enough.
But so there's going to be two lines. You can see a line on the diagram on the left. If you scroll down, I think you can see one with two lines. And those lines, they both start at where that circle is, and then they end somewhere. And you have to find the places where the two lines overlap, and then find all the places where they overlap, and then find the one that's the least far
from the origin.
Calculating the Manhattan distance,
which is just the basically the distance of this path, right?
Yeah. So in that example, it would be 1, 2, 3, 4, 5, 6, I think, because you're going up and diagonally. So it's like 1 across, 1 up, 1 across, 1 up, 1 across, 1 up. So that's 6.
Yeah.
I think.
Yeah, so you can also just do it like it's 3 and 3 from the origin.
Yeah, it's how many blocks you have to walk, which is why it's called the Manhattan distance.
Yeah.
If it was
so what's interesting is that you'll see is, I mean, the interesting thing about this is that I immediately thought of coordinates on a graph.
Me too. Yeah.
So 0, 0 being here, and in this example, this point is 3, 3.
Yeah.
This point is 4, 6, is it, or something? I can't remember exactly.
Yeah, whatever. Yeah, it looks like it's 2 more. Sort of.
And the interesting thing there is that the Manhattan distance is literally just the two of those things summed.
Yeah.
Which we'll probably come back to.
Yeah.
It in a second. So that's of interest.
That's exactly how. So how
did you go about? So there are two problems here, right? One is you've got to plot. You've got to know where the line goes, and then you've got to know where they intersect.
Yes.
So, what was your sort of? What was your play here?
What I did was I very crudely created a giant array of all of the coordinates that line passes through. So if you go back to the picture, so if you highlight there, so this one would be 0, 0.
Yeah.
Then it would go to 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 0.
Yeah.
Up to whatever that is, so it's 8, 0. Then it would be 8, 1,
Yeah.
8, 2. And you just get a giant array with all those things in. And I do that for each path. And then what I did was I intersected all those coordinates. So like what ones do they have in common? You just use intersection, which gave me all of the cross points.
Yeah. So you're literally, but you're path following basically. You're saying from here I need to go R8.
Yeah.
So then I'm going to go.
Right,
I've got 7, 6, 5, 4, 3, 2, 1, 0, and then I know I'm at the end, and then go up.
Yeah.
Yeah. So I think that's interesting because I think that helps you in the second part more than the way I did it.
Yes. So I think I got lucky because you don't know what the second part is until
you've done part one.
It, yeah.
So the way I did it was I wanted to calculate all of the end points of each line, I guess you could say.
Mm.
But then, which is actually relatively easy, but then filling them in, whether that's in KDB or just generally, I don't know, ended up being the more complicated bit. So I was saying here, I'm at 0, 0, I'm going to go right 8. So the end of that line is at 8, 0.
Mm.
Then I'm going to go up 5, it's at 8, 5.
Right. So you ended up with
3, 5.
1, 2, 3, 4, 5 coordinates.
I'd have 0, 0 plus the number of instructions basically.
Yes.
Basically translating the instructions into coordinates.
And then in an additional step, did you translate them to the thing that I said, which is every individual
and then
step.
You have to fill between them.
That's interesting. So I didn't do that
because you'd already done it.
Step, yeah. So I just go straight.
Yeah, so which I think is why it's better.
So let's have a look. See how that. So if we scroll to the bottom, So this time I've written some.
These are some of the ones that they put in, was it?
Yeah, these are some of the examples. Yeah. So distance from origin
to closest intersection.
Yeah. So it takes the instructions and it parses them, and then it maps over them. So parsing them just gets them into arrays of those things, and then then I have a handy function which is instructions to coordinates, and obviously you've got coordinates 1 and 2. So by the time you get to line 46, you've got coordinates 1 and 2. Have you seen that syntax before?
Yeah, so it's like two variables from a.
Yeah. So line 47, 48, and 49 that's all basically one line of code. So this is this pipe operator thing. So
is that what just saying the line continues? Is it?
It's like,
or is it like doing this and then this on each of these?
It takes instruction. It's as if you've called parse instructions open bracket instructions.
Ah, okay.
And then the output of whatever happens goes into the first parameter of maps, and then it's as if you've said whatever the output of that was, enum.map, the output of that comma.
Yeah,
function.
okay.
So like the first.
Yeah, it's like the Unix pipe, basically. Then.
Yeah, it's kind of like the Unix pipe, and it because you don't have there's no dot operator in this language, so you can't do say like my string dot trim, not a thing. So string dot trim will be it's just sort of like a static function, and then you could say my string and then pipe in and
like
then
this,
pipe,
I guess.
And then pipe. Yeah. So I've done it there. So like you've got a string and then it's trimmed. So,
interesting. Yeah, okay. That's an interesting. Yeah, that syntax seems a little verbose in that example, right?
It's weird. I quite like it over time, but and it also has a lot of pattern matching stuff. But so from 46 to 49, I parse the instructions, and then I run this magical instructions to coordinates, which is a reduce. Oh god, I was feeling brave. So for each instruction, you're building the coordinates.
So this is building the path, I assume, right?
Yeah. So you've got you start off with
you're splitting out the direction and the value amount to go, right?
Yeah.
And then you're parsing the magnitude as an integer.
Yeah.
And then what is this LM0 doing? Is that your coordinate array or something?
No, so LM0 is when you have a tuple type in this language. It's just getting the leftmost thing from the tuple. There's a tuple on line 35 above.
This.
So yeah, it must be.
So this is 0. This is 0. This is.
I don't know
1.
why I have to do that, but it must just return a tuple for some reason. I don't know. And so then you've got but basically you're getting the direction, and then you get the magnitude as a number, and so then it adds and then it returns your existing whatever coordinates you already have that you're building, and then that's just an array append, and then the next coordinate for the instruction, and that is
here.
Yeah. So
so this is taking.
Yeah. So it literally takes it takes a direction, a magnitude, and all the coordinates you have so far. It gets the last coordinates,
or
0, 0 if they're not there. So that's your x and y.
What's this? As it's like a count.
It's like a range.
Yeah,
so from 1 to magnitude, and then I'm mapping over that, and for each one of those, I just
build
so it's like x plus steps or y.
Oh yeah. Oh that makes sense.
And then that's it, I think. Or what was the code? But yeah, like that.
Well, that's just x plus y.
I'll say no 51.
That's
so
your
then once
intersection.
we've got coordinates 1 and 2, which is like the fullest coordinate, you just intersect them, and then calculate the of the ones that cross. You calculate the Manhattan distance. You sort them, and you get the first, which is the shortest.
Yep.
That's it.
Yeah,
I was quite happy with that. Actually, even reading back, I'm
it makes sense.
Reasonably pleased.
It makes a lot of sense. I do.
What am I about to witness? I'm nervous.
So this is So this there's a lot of bad use of
There's
KDB.
a lot of bad. There's a lot of bad.
There's a lot of bad. Full stop.
Oh goodness.
So this is. So functions are first class citizens in KDB.
Yeah.
So this is building a dictionary or a map, but dictionary in KDB parlance of if based on the operator, what index. So my coordinates are tuples as well, but we don't have that explicit concept in KDB. It's just a list. So if I see a right, I'm going to update the x coordinate, which is the 0th element of the array, and I'm going to plus.
So is that a function? Is that
plus is the function?
Is that a function which adds 0?
No. So in this example, no. It's not like the partial functions I used before.
Yeah, because that looks quite similar.
Yeah. So this is just the list syntax. So this is a list to map. So this list is for long to give us the values of the 4 keys.
Yeah.
So that our key is set to a list of 0 and plus.
So you can literally have the plus operator in a list.
Yeah.
That's mental. Okay.
Any function you can do that with.
Because it's a function.
Yeah.
Okay.
So that's the same here. So then if it's an up, it's the y coordinate, which is the first element of the array.
Right.
2, and I'm going to do a plus to it.
Right.
You'll see why that works in a minute.
0 and 1 is x is whether it's an x or a y
element of the list,
index,
and then whether I'm adding to go up or subtracting to go down.
Okay.
The build coord here is how this actually gets operated on. So this build coord will use this map, which has been translated into op, which I'll show you in a minute, and it's taking the coordinate that you have, and it's taking the first element of the list, like your lm bracket 0, and the lm and the second element, and the amount. And so what this at operation does is called apply. So in a list, you tell it the index you want to work on, the function you want to execute with, and then the second parameter to the function. So my coordinate is, say, 0, 0.
Yeah.
So that would be 0, 0 in here. You take the op 0, which in, say, is the 0th element, so it would be the first 0.
Yeah.
I then want to plus to that value the value of move.
Right.
So by doing that, that will give us part 1, which for all it's very ugly. But basically, this is giving us this is doing the parsing of the input data.
Yeah.
So I'm splitting each line by the comma.
Yeah.
So it's a comma split.
Yeah.
And then this is just doing the parsing, which I'm not going to go into a lot of detail of why I'm doing this the way this is. It's a bit of a hack to write less code, which again, this is still in my early days where I was feeling keen, but there's no real benefit of this. I'm just saying, take the first character of each of the inputs, and then remove the first character for each of the inputs, and then cast the first element into a symbol, which will be this instruction, and the rest of it as an integer.
Right.
That's all that is doing. But it
That's
looks ridiculous, yeah.
That's mad.
And then what I'm translating this into is, this is awful. It's actually very hard to read back. At this point, I'm basically, what I'm trying to do, I think, is, I know what I'm doing. So because I've split everything up, so every coordinate, every original instruction now is a symbol of the R, the U, the L, or the D, and then an integer value. So I have a symbol which is what way am I moving and the integer to move.
Yeah.
What I've done here is I've then translated that. I've basically done a lookup in this map.
Yeah.
So I've translated all of the characters now into the operations I need to perform.
Right. And
then I've added 0 to the front,
so
of each wire.
So you end up with those coordinates you mentioned, which are the sort of turning points of the wire.
Well, no, so all this is doing is giving me the operations. Then to actually execute all the coordinates, that's this line.
Right.
And then this is the ugliness to give me all of the wires, and then I just do an intersection as well, basically. That's what this is doing. But this syntax is all I had to do to be able to get from the corners everything in between.
It is so mental how different this is to any other I'm pretty well versed in a lot of languages, but this is nuts. Tough. Yeah.
This isn't, I would also say this isn't nice KDB either. Like some people get off on enjoying writing code like this. I don't really enjoy it because it's very hard to understand what's going on.
Yeah.
But it's just the terseness of it.
Yeah, it's been a week and I can see you're already
regretting it. So so roughly what I'm doing is I've got my coordinates and I now need to work out what's the difference between them.
Yeah.
So I'd be like, so if we're at 0, 1, 0, 3, the delta between that is 2 in the y-axis. And then I need to use this, we have this, like your ... operator in Elixir, we have till.
Right.
So you till of a value and it'll give you a range.
Yeah.
But then the disadvantage with this till is that it doesn't like negative numbers. So you can't go from like 0 to -10 for whatever reason. So I have to just do it positively and negate it, which is what this is doing up here. So it's saying if x is greater than 1, if x is greater than 0,
less than 0.
Yeah. So this is another interesting syntax. So first thing I'm doing is till the number, but I have to plus 1 because it does it always from 0.
Yeah.
So I want to do plus it from 1 and then drop off the first one because I was getting an issue of double counting the same coordinate.
Yeah.
And then what this is doing is, again, a bit controversial. So this is a list of 2 elements. One is this double colon, which means is the identity function. So anything you pass into it, it'll give you back out.
Yeah.
And the second element is the negation. And then what I'm doing is using this syntax, which is saying, well, is x less than 0? If that's true, which will give me a 1, it'll then index into this list and give me this, and then apply that to my result here on the right-hand side.
Dear Lord, that is so complicated. And then I see on line 29, I think I do understand. So you get all your intersections. Absolute is part of the Manhattan business, and then
so this looks very similar to your bit at the end there.
Sum them up and then get
find the smallest one. Yeah. So this screwed me over for part 2, and obviously, as you can tell, it's not pleasant.
What was part 2? If we go back to the part 2, minimise the signal delay. I don't actually remember this at all.
So this is now step count. I think so. You've got to count the number of steps to. It's the short now rather than the Manhattan distance. It's now the shortest number of steps.
So wherever your intersections are, which one had the combined smallest piece of wire to get there?
To the first intersection, yeah.
Fuse combined.
Was the fuse combined steps the wires must take to reach an intersection? So it's from 0, to an intersection, which is the shortest, which takes the shortest amount of time.
And the least hops.
Yeah, so it's not Manhattan distance anymore.
Cool.
So I can't.
And imagine this is just glorious because I'm already in pretty good shape.
Yeah, you're in pretty. So a lot of this should be repeated from before.
Yeah, that all looks the so now instead I've got steps. So this is the only bit that's changed. In fact, the only bit that's changed is line 63. I'm just calling a different function. So
so steps until intersection, which is here.
So given coordinates 1, 2, get the cross coordinates, and then for each, so cross coordinates is
the intersecting coordinate points, right?
Yeah, and then for each of those,
work out the steps from.
So I don't know what I meant here. So from steps and so no, no.
Steps until intersection.
So what did I mean there? Coordinates 1.
So your coordinate here is the intersecting coordinate.
Oh, right.
And
so
then you've got something you've passed
in coordinates 1, which is like, say, the first wire, how many steps is it until that coordinate?
Until that intersection,
and then, until that, yeah.
And then you do that for each wire.
And then add 2, obviously. No, I don't know.
Just to get the right number.
Just to get the right number. It will be one of those ones where it's come out and I'm like, it's working, but it's 2 off. Add 2.
Yeah.
There will be a reason.
But it's also that's why you see like a lot of me like dropping 1 off a list because I'm like, that's counted twice.
You don't need that. But it will be because each of them will be counting 1 too little.
Yeah. The intersection point probably. It might be 1 short of the intersection or something like that.
Yeah, I don't know why.
Or 1 short from the start. Maybe.
I don't know.
Anyway.
And then steps until is
here.
Yeah, coordinates with index. Otherwise you can't reference the index. So with index takes an array and returns an array of the same length but with tuples, and each of those tuples, one of the things in it is the value that was in the array, and one of those things is the index.
Ah, interesting.
Which is a bit weird because in most of these sort of functions I use, you can optionally just add a second parameter, and that's just the index, which is much easier than that. But you can't do that apparently. So then you get so then it's like I'll find that coordinate, and then lm1 is just the index.
Yeah.
So it's like,
give me the index. Basically.
So you could almost ignore 43 and 40. Yeah, exactly. Give me the index. So it's just like find the coordinate which matches, and what index was that?
Yeah. Yeah.
I think there's a find index function, which was probably.
Oh, yeah.
There's a find underscore index function which would do this without line 43 and 45. But I am still learning. I found it since, so you could definitely. But yeah, that was pretty straightforward, really.
Yeah, so I think that was I noticed because a guy worked did it the same way as you, because he already had the paths.
It's
a lot easier.
Although don't you also have them?
Yeah. So what the hell happened?
That's what I'm thinking. I'm like you.
No. Yeah, I did. The problem was. So I think the thing is, I've modified this slightly to be easier to use in part 2, because this now does look easier. So what have I done? So all of this is the same as this. The difference is that I actually need to keep the trace elements now, because I've got the trace is the actual wires, whereas before I was calculating all of the wires and then immediately intersecting them.
Right.
So that to here. So this intersections variable and this intersection variable are the same.
Yeah.
And then
over there, you still have the traces too, right? Yeah. So you've just basically extracted a variable except for.
So now what I've had to do is some god awful. I mean, this is not pleasant.
Oh no, yeah, you have exactly extracted a variable. Yeah. Okay. Yeah,
so
more or less, there's some differences.
Again, we'd have to run it to see it, but basically, so my trace. I'm having to look up each of the intersections. So I'm doing exactly the same thing, bizarrely. It's just not very obvious. I'm using the index of where the intersection is in each wire.
Yeah.
Just take a step back. That's what that's giving me.
Okay.
For each of the trace elements. So what I'm doing is for every trace element, tell me where the intersection coordinate exactly matches everything in here.
Yeah.
And then that'll give me a list of trues and falses. And then where is a KDB keyword that will just convert a list of booleans where things are true to the index where it was true.
Gosh. Okay.
So if you've got an array of 10 booleans and the fifth one is true,
Yeah.
you then do where on it, and it'll give you a list. It'll give you 5.
Right. So
Or
then
14.
what do you end up with? You end up with the...
So that gives me the list, the distances to each intersection for each trace.
Yeah.
And then I'm summing them. And then I have to... This raise is like a get out for when you've got a weird object shape and you just want to flatten it. So then you can do minimum of it.
Okay.
So it's a bit of a hack. But yeah,
similar.
so it is similar. Like that. This bit I would say is similar. It's just it took me a long time to get to this because I think the way I'd done this initially, I was trying not to have to build the trace again, but obviously that's impossible.
Yeah.
I was like, well, I've got the coordinates. I should just be able to work out the distance, but I couldn't.
That's not horrific, though.
Well, the syntax is. I'm pretty ashamed of this syntax. There's definitely nicer ways.
Is this shameful? It looks like someone. It looks like how before I learnt to code when I saw hackers on TV. This is even now feels like that for me, where it's like if I was watching like a film and someone started typing this in, I'd be like, that's clearly not coding. They've just made up their own thing. It is mental.
There are nicer ways to write this. So this in particular. So these operators are like nesting operators. So it's like I want to run this function within, because I've got a list of lists. I want to operate this. I want to use this operator within the elements within the lists. So I've got because I've got a list. I've got one list, and that has a list of lists, and within each coordinate is a list. So I've got like 3 nested lists. I want to get into the lists twice. And then just to look at the coordinates. Yes. If that makes sense.
Yeah, I know what you mean. I know.
I have explained it terribly.
It's like if you're mapping, it's like having a map and a map and a map, but not.
Yeah. But so because this tilde is like, it's not, it's like object equals. Not that we really have objects. So it's like, it's, I don't know how to describe it. So we have equals, which matches.
References?
No, we don't really have references on.
Oh dear Lord.
I don't really know how to describe it.
Can you give an example of 2 things which would and wouldn't match?
Yeah, so zero integer. Oh, can I give an example? So for atoms, equals and tilde are basically the same, but for lists, because all of KDB operations work on lists, if you had a list of 0 to 5, so 0, 1, 2, 3, 4, 5, and you did 0 equals 0, 1, 2, 3, 4, 5, it would test the equality of each individual element.
Right.
But with lists, sometimes you want to just say, is this list the same list?
Right.
So if you had like 0, 1 equals 0, 1, standard equal sign, it would do the equality comparison of the zeros and the 1, and it would give you a list back saying, well...
True.
Yeah.
Mm-hmm.
But actually, in this case, I want to know, does the coordinate match? So I want to say, is 0, 0 equal to...
So like, I would phrase that, and this is probably not right for Q.
No, please do.
The operations by default are like vectorized as the word, so they always operate on like a list basis, and this is like a non-vectorized equality, basically, where it's like...
Yeah, it's like just taking the object as a whole. I use the word object loosely, but it's taking the whole thing, the whole object element, and saying, can I equate this to my other thing?
Yeah, so the whole data structure.
Yeah.
Just compare.
So then you can do like again with maps, you use tilde if you had map A and map B and you wanted to see if they were the same map. And by the same map, I mean look exactly the same, not be the same reference.
Yeah, so they can be 2 instances, well, not have instances, but you could define them twice and it would still say true.
Yeah, so there's no... So everything's by value. So I'm saying I've created dictionary A, map A and map B, tell me if they're the same.
That is a weird consequence of having operations which work on an element by element basis by default. Yeah. And basically you then need to say, no, do that.
Yeah.
Cool. What was the next one? This one was, there's a password. There are certain rules about, the password only has numbers, or so it's like a pin, and there are certain rules about it. So it was going from left to right, digits never decrease, 2 adjacent values are the same. I'm reading this backwards, it's up a bit. So it's a 6-digit number.
The value is within the range which they specify somewhere.
2 adjacent digits, and from left to right, the numbers never get smaller.
Yeah.
They only ever increase or stay the same.
Yeah, I'm going to make a point here now. I think the part 2 was very, very hard to understand to get this right.
I don't remember, but we'll find out.
We'll come back.
So
how many passwords within the given range in your puzzle input meet this criteria?
Right.
So we'll go to use first.
So
I
this
think
is
your
going to be
range.
poetry in motion because I've more or less I was getting there with.
Yeah.
So yeah, the range that I was given must have been this.
So there's underscore. What's that about? That's just a way to write.
I think there's an auto formatter. I wouldn't have written that, so I think that must be. I've seen that's. I think that's Ruby syntax.
What to be
So
have
this
big
whole
numbers?
language, someone pointed it out to me. I think it was someone pointed it out. Was it you? Yeah, it was you. But it is basically.
It reminded me of Ruby, even though I don't know Ruby.
Most of it, and that is also valid in Ruby. It's like a comma, so it's like
Interesting.
68,000.
Yeah.
68,000. I can't say that, but yeah. So for that range, for each of them, is it a valid password? So if you on line 40, so just like find the ones that are valid, and then on line 45, I just take the length of that.
Oh yeah, okay, yeah.
So that's it. So then
we
is
work
valid
out.
password. This is poetry in mode. I was happy with this one. It
Very
has
English reading.
If it has two adjacent digits and it's never increasing, so two adjacent digits, I think was pretty straightforward. So
you convert the number to a list.
so that's just an
Is
array.
that built in, or did you write?
No, I've had
that?
to write that.
Ooh. Rem.
Rem is remainder,
Remainder.
so it's basically mod, but they don't have a mod operator, so it's basically mod. It's
And
basically the cent sign.
you're dividing it by 10 to get all of the bits inside of it.
Yeah, so I'm just dividing. Wait, does it call itself again? Yes, so it's recursive as well on the left. On
Yeah,
9.
yeah.
So I divide by 10, and then so that basically removes a number from the right hand side.
Yeah.
And then I'm like plus mod by 10, which gets the last. So that's just the last digit. So it will create an array with the last digit in and append it to whatever the answer is for the remaining number.
Yeah. Interesting.
And then so on line 23, if you highlight there, so that gets just basically if your password was 1 2 3 4 5 6, you would get an array with 1 2 3 4 5 6.
Yeah.
And so then
We all had this problem.
So then which was just sort of moving data around. So then it says get adjacent pairs. So
chunk, so basically get two elements of each. Split the number up into the list into two element pairs.
Yeah.
Right?
So if it was 1 2 3 4 5 6, you would get 1 2 in an
3,
array,
4.
then 3 4 in an array, then 5 6 in an array.
And then you've got only pairs.
Only pairs. So
Oh, is that ignoring if it's a weird?
why is that?
If you've got. I don't think you need that because I think all of the numbers in there would have 6 elements. I think maybe you wrote that before you read the input.
Maybe that was. I don't know why I've done that. And then in the next one, I say drop the first thing. So you've now got if you had 1 2 3 4 5 6, you've now got 2 3 4 5 6, and then I chunk. Oh, that's maybe why every 2. So then you would get 2 3 4 5. So you basically get the other pairs that you didn't have. So the first step was 1 2, then 3 4, then 5 6, and then this one's 2 3 4 5
and 6.
6. And that's not a pair, so that would get eliminated. So you end up with all the 2s, basically, all the adjacent digits, which is what's called adjacent pairs. And then it says for all of those, we weren't doing that one. We were doing this one.
Here,
32.
Oh, sorry.
So
So you've got your adjacent pairs now.
Are any of them equal?
And why is... Oh, right.
Because they're adjacent. So if you've got all the pairs, all the sort of adjacent digits that are next to each other, and it's like for X and Y, are any of them equal? So like, for example, if it started 2 2, it would be true. And it's any, so it's just, are there any?
And you got your triple equals here?
Yeah, I didn't think triple equals was valid syntax.
It's a JavaScript thing, isn't it?
It's a JavaScript thing. I'm surprised that runs, but never mind. Apparently it did. 25... So is never decreasing, is password, number to list, adjacent pairs, so it's all reused code. And then it says for all of them, so now you've just got the pairs the same. For all of them...
Return all of them where...
So for all of...
the pairs, the first element of the pair is lower than the second.
So all and any return a boolean. So always just like, are all of the pairs, is the left-hand one in the pair small, lower, or equal to the right-hand one? So it's literally checking all the pairs, is the one on the left smaller than the one on the right.
Yeah.
Which means it's never decreasing.
So how is that true?
So if you had like...
Because if you had one... Well, how does that stop you having 1 2 4 5... 1 2 1 3?
So there would be a pair 2 1.
Ah, yeah, because you're doing it. Yeah, okay. Yeah.
And then that's it. And then if you go back to 38, that was the... So those two are called there, and then it was... And then, no, not 38, 36.
Oh, right, sorry.
And then 42, so filters and then length. So that's it. So it's pretty...
Filters. Okay.
I mean, to be honest, if you ignore the detail of those functions, really, it's just filter if it's a valid password, and then his valid password's just defined.
Yeah. That's quite nice.
Yeah, it's pretty happy with that.
Yeah.
What was...
I can't remember. I'm
sure it will be easy to understand.
Easy to read. It's not too bad, actually.
Okay.
Not too bad. I'm probably happy with this one.
Should we see if I can understand it? Probably not. You take the numbers and put them into longs. I don't know what the dash means. Oh, no, dash separated.
Yeah. So it was this. This is the input here. So this is my input. Split it. Cast them both into integers.
And then, oh my god, you reverse?
Yeah, so I flip them around, and then this is basically, the minus takes two operators, and by putting it in brackets and putting a dot, it'll take a list and apply the first element as the first parameter and the second element as the second parameter. Right. So by reversing it, it's basically doing 6, 5, 7, 4, 7, 4 minus 1, 8, 3, 5, 6, 4.
Right.
And then I'm doing a till of it, so that's giving me all the entries between these two numbers.
Right.
How did you do? Oh, you did it just all on.
They have dot dot built in.
Did you? Where was your dot dot? Where did you calculate all of the? Oh, it's here. Sorry. Yeah. Sorry. Apologies.
Is that basically the same code?
Yeah. That till. Mental. Well, till does that. Yeah.
Till does that, but you've.
I guess. Yeah. I mean, if I'd put this in here, I would have just done till. I would have just typed it in the other, like you just typed in. Yeah, if you had to load that in off out of a string, you'd have to parse it and all that stuff, right? I don't even know how. And then so that gives me the range. That gives me the range. I just add it to the first one to give me all of the potential passwords.
Yeah,
this is an interesting way of converting the passwords into integers to give me the list of integers for each number. So this is converting them all in. So all these were integers. I'm now converting them back into strings, and then this is a list of all the numbers.
Right.
And each element of the number, its index is obviously the integer of the number it is. So it's a list of 0 to 9, and if you pick 3 of that, its index is 3.
Mm-hmm.
So this is basically doing a find. So for each number that I've given it, it's going to translate the string value of the number into the index, which also happens to be its number.
Gosh.
Which is a weird way of doing it, but it's quite an efficient way in KDB, just a weird oddity, I guess.
Yeah.
So this is like the find operator. So it tries to find all of the elements on one side and the other side and give you the index where it matches. Just happens to give me the same thing. So now I have a list of lists of integers. So we're in the same place.
Yeah.
I think we're all going to be very similar. So adjacent this is deltas. So this gives me, for a list of integers, what's the difference between each one?
Yeah.
Iterating through.
Okay, that's pretty neat.
And so if there's any of the 0...
Oh, that's actually much better than the way I did it.
Well,
I think. That's actually a much cleverer way.
So then
that's actually a much better technique in general, actually. So you basically... You've gone through and you found all the differences, and then you've said if none of them are 0, where 0 in...
Yeah, so if there's any of them, if there's a 0 in there, that means there's some adjacent.
Yeah. So and that's kind of an any.
Yeah. And then where, like we said before, gives me the elements in my whole list where that's true. Yeah. So I know that's the passwords that have adjacency. And then incrementing... There's actually a better way to do this, but I did it this way, which is I sort them all and then check if they match. So if them or each sorted is the same as they were, then they're incrementing.
That's clever as well.
It's a weird way of doing it, I guess.
No, it's simpler.
Maybe.
Yeah, I quite like that. You're basically like, that's actually a much better way of defining that. I could have, in my code would be better for that as well. You're basically like, even in where I had it arrays of numbers, or do you have arrays of numbers?
Yeah, I do have arrays of numbers.
So you're like...
So I'm sorting each array.
Is the sorted array the same as the array? And if the answer is no, you're basically... both of those approaches are better.
They're interesting. I wonder if that's based on the way that KDB works, why that seemed to be the way...
I didn't even think...
No, I'm wondering why I went this route. Obviously, we don't know. But...
It's funny, though, because this route, especially the second route, is definitely open to me. And actually, if you go back to my code is never decreasing. I wouldn't need you to have done adjacent pairs, though. I'd just say number to list, and then I'd say for all of them, if you sort it, is it equal to the original?
Yeah.
So it'd actually probably been easier.
Yeah.
I don't know. Well,
it's difficult to know. It's obviously easy now to look back, but that's how I did it.
That was interesting.
And then, so I've calculated them separately. So then I've used this all passwords as lists in both. So then I've just intersected them to tell me which ones is it both true, and then count.
Yeah.
So that's
cool.
That's it.
Well,
So this, I guess I should point out here. So this is that equals that we were just talking about.
Yeah.
And then because these two lists are the same, I put this character in, which is telling KDB to do the equality check index wise. So it'll do the tilde check, the 0 element and the 0 element of each side, and then the first element, second element, and it'll give me a list of the booleans.
What will it do otherwise? It doesn't care about ordering.
Well, because this is a tilde, it would, if you didn't have this, it would check the whole list the same as the whole list, because the tilde is a non-vectorized operation.
Right.
And so basically, I've put this character in to tell it to vectorize
the top level.
Yeah, and because the elements are the same the same length, I can say it's like a zip. Is it a zip?
You have you basically have an array of arrays, and you're doing an equals operation on the inner arrays. But on the top level, you're running that in a vectorized way across all those arrays.
Yeah.
Goodness me.
Weird. Quite nice.
That does make sense.
So that's
pretty short. You've got to give
I think I was pretty. I remember feeling pretty happy about this one.
Yeah, but, what was the second part?
They add an extra. So this is the issue I had with this. Is I think this wasn't very clear.
This was quite hard. This one.
Yeah.
2 adjacent matching digits are not part of a large. So it's 2 and only 2. So you can't. So 1111 doesn't. So if you had one like 1111 2 3 4, that doesn't count because the ones there's 3 ones and you need 2 ones.
Yeah. So I didn't get that from this.
They do have examples there. I didn't know what they meant. I just found it hard.
I found it very hard to understand why this one passed.
Oh, yeah, no. Oh, because it's got 2-2.
Yeah, but that wasn't very clear to me.
No. It does say, though, in their defence, it still contains a double 2-2.
Yeah, but I don't know. It's easy now. I can't think now why I found it difficult.
Something. So how did I solve that?
Is that this one?
Yeah, it's an innocent. Wow.
So it looks similar.
Has 2 adjacent digits, not in a larger group, line 37. It's not the same. It's otherwise the same, other than this, calling this function.
Adjacent nums, length, adjacent numbers. Right, so you've done adjacent numbers now rather than adjacent lists, pairs.
Oh, okay, so that has changed. Adjacent numbers. Oh my goodness.
So split while.
Right, so if we put an example to this, so if you put in 1 1 2 3 4 5 6 no 5 1 1 2 3 4 5, then it's split while on that. It would say split while, and then it's saying when n is equal to the first number in the list, which is 1. So then you'll get, I can't remember how many ones I put in. You'll
2.
get 1 1.
Yeah.
And then you'll get 2 3 4 5 6. So it splits the list.
Okay.
By that.
So then you're trying to find how many of each number are adjacent.
Yeah.
So you're saying if there are 3, then you get 3 in the rest of the list, and then you apply it again on the list.
Yeah, so then you've got your adjacent numbers, which is 1 1 on the left, and then you just rerun this function on the rest of the list. So then, and then you say, are any of the? So basically, it finds all the groups that are the same, and then you say, are any of those of length 2?
Yeah.
And if the answer is yes, which I think actually is.
Yeah, I just don't think that was that clear from this. Like it said, not part of a larger group of matching digits, but nowhere was it. I think 100% explicit that it meant you were expecting exactly a pair. But maybe that's just me.
I think I was okay. I have struggled with others. How did you solve this one?
It took me a long time. But
all the same.
Everything's all the same. The difference is here. So I ended up doing it the same way you did it.
So you've grouped.
So basically, yeah. So what I've done here, I've got all of the passwords that match the original constraint. And then what I'm saying is, because it's a list, group basically groups all of the elements within it. So if you've got 1 1 2 3 4 5, like you said before, group will give you a map back with each element in the list with how many times that occurred.
That's good.
So then it's just a case of saying, well, where is it to?
How does it know that they're adjacent?
Because I have it previously, because I've already filtered out by that. So here I've already filtered out by adjacent incrementing.
Wait, what about like 1 1 2 2 2 1? Would that not give you 3 for ones, but it's valid?
But that would already be discounted because it wouldn't be incrementing.
Well, you get away with it because it's incrementing.
I think so, yeah. Yeah,
Yeah, you do.
yeah.
Jesus.
That's the killer.
That's mad.
Otherwise, that wouldn't work.
That wouldn't work otherwise, yeah.
Yeah.
Did you know that when you wrote? That was not obvious to me at all. But yeah, the incrementing rule.
Well, yeah. So I from what I remember now, I was trying to solve it by applying that rule to everything and then intersecting of all three constraints. But I was just banging my head against this issue.
You've used the constraint that they have to be incrementing
to then allow.
That's actually more efficient. That's very efficient.
Yeah, it does. Yeah, it seemed to work okay.
So if tomorrow they said they change the increment, they remove the incrementing rule, then you'd have to go back to the drawing board, basically.
Yeah. So then I think what group gives you is the index where they occurred. So then you'd have to use deltas on that to then see if there's any increment, whether they're adjacent. If you couldn't use this adjacency rule for whatever reason, or if they changed,
that would be quite tough. But that's cool.
Yeah.
Okay.
So day 6. Do you remember this one? Feels like months ago.
It does feel like a long time ago.
I found this one quite hard.
Yes.
So it's basically a tree, a tree.
I think it's a graph.
Graph.
Isn't it?
That's the one you want. Yeah.
Yeah. So it's
basically, it looks like a Git. Every Git example you read looks a lot like this. Because they're like, if you do a commit C to D,
it does, doesn't it?
And then it's like this, and then you do a branch to I, and it looks like this, and then.
So each of these letters are moons, and I can't remember what part 1 of the question was. What was part 1?
Part 1 is, what is the total number of direct and indirect orbits in your map data? So, the count of that is, because D is directly orbiting C.
Yeah. So I is also orbiting C because it's orbiting around D.
Yeah, so it's indirect. So if you orbit something, everything that thing orbits, you also orbit.
Yeah, so com's like the sun, and B's orbiting the sun, and G's orbiting B, and H is orbiting G. So like H is indirectly orbiting around the sun.
Yeah, exactly, yeah.
Cool. Let's have a look at some code then. How did you...
Oh, do you want me to go first? I can't remember. It's a blur.
We can...
Oh yeah, so this is my part 1.
Oh, that's beautiful.
I have to try and remember what was going on here.
What is store? What's store? Oh,
So store's a dictionary or a map,
okay.
And then this is a cheat way of basically this is globally stored. So this is a way of just clearing it every time you run because I cheated and just stored everything in a global. So the way I've done this is. And I think the problem with this question I've just realised is that although it makes this first one quite easy to solve, the second part screwed me big time. So I parse out the data. So I'm going to split it on the bracket, and then that gives you whatever the input look like. Yeah, so if you split each line on the bracket, you've got the parent on the left and the child on the right.
Yeah,
and then I'm storing for each node its children.
Yeah.
So this store, after you've reloaded this, would be like, in this visualization, the map would have a key of B, and it would have G and C as the value.
Right.
And then C would be the key and have D as the value.
Yeah.
Etc.
Yeah.
So, and then what I've done here is I'm basically, although it's not very obvious from here, I'm iterating for each value.
Yeah.
I'm basically keep looking up in the store until there's no children. So I'm basically descending from each point downwards. So this is saying, give me all of the values of the map, so all the right hand side, and then make it a single list. Raise just flattens the structure, and then I'm doing a lookup into the store for each of those, and then I'm doing this operator, which is like a for loop, but it keeps all of the output for each iteration. Right. So if I remember before, I used the / like here, which is like loop until the output is consistent, stops changing. The / just gives you the end result, whereas / gives you every intermediary result.
Right.
So when I'm traversing the tree, it will give me all of the values. So if I pass in C, it will then go into the dictionary, look for the key of C, that'll give me D. And then it'll go back to the dictionary, look for D, E, and I. Right. So from any letter you give it, it will then give you the subtree.
Wow. That's quite succinct, really.
And then you make it, you flatten it out with this raise, and then you just count how many that was.
Right. So you're basically traversing the graph, getting all the chains of how you can go down the graph, and then flatten it and count it.
Yeah.
Okay. Cool.
Well summarised, considering you didn't write it. You summarised it better than me. So where's run here?
We trim. So I think
that's just parsing.
So parsing, yeah.
This is the magic.
And then I'm going to see if I can. So I've also some flattening. So I flatten the orbits. Wait, how did I parse the orbits?
So you've got a separate function.
I've got a separate function. So I've parsed the orbits probably
the same way.
Yeah.
Split it on the bracket. And then you've done count, which goes into here. So you've flattened it, which I assume gives you... I don't know what flatten would do with a list like that. If you've taken... You split on the new line. And for each orbit, split it. So then each element's got 2...
Yes. So it's an array
of arrays
where each inner array is of length 2.
And then map set can accept that, can it? And gives the one left one as the key and the right one as the value?
I think if I'm reading this right, so then I'll have everything that was on the left and everything was on the right, and then I put them all in a map set. So now I've got a unique list of moons. I think that's all that gets you to. So yeah, unique objects. I've called the variable. So,
okay.
So it's just what moons there are. So it'll be like A, B, C, D.
And then because it's a set, you lose the distinct.
Yeah,
you get basically a
default.
distinct. Yeah, okay. Sorry, I over engineered that one.
And then for each of those unique objects,
calculate the orbit. So for each moon or object, I've called it. I'm passing in all the orbits twice because of recursion. And now this is your Haskell looking notation.
Yeah. So I think if you have none left to process, and the answer is 0 on the count. If you find,
is that everything except? What's that? Everything or nothing, or you don't care?
So that's the cons operator, which you may remember. I think it's a colon, or it might be a line in Haskell as well. So it's a pattern matching thing. So it's an array where the first element of the array is an array with O and object, and the rest of the list is underscore. And underscore means you just don't care.
Yeah.
So
I knew it meant didn't care. I just couldn't remember this.
So this will match. So if the object you're looking at, say you're looking at A, if the first element in the second argument, the right hand is equal to that. So because they're both called object, I'm not going to point at the screen, but that and that are the same, basically. Yeah.
Oh, okay. So it's actually doing an equality.
Yeah, it's actually matching it. Yeah. So if they were different, then it wouldn't match, and then you'd actually go through to line 18 instead. So if that's the case, then you want to recalculate everything again, but this time you're starting from what was over on the left hand side, so O.
Yeah.
Which is and then I think when I ran it, it didn't. A 1+ is because you're tallying, you're adding.
You've got to count yourself, right?
Yeah, you're counting yourself, and then the bottom one's like you found one. There are no matches for it, so then you just keep going through the first element didn't match, so you're basically
doing like a depth first search almost, right?
Yes,
because you're going all the way down the head, and then back up, and then down the tail,
and then that calculates it probably not super efficiently, but
it's basically the same.
It's quite similar, yeah.
Well, I would say basically the same. That's unfair, but it is very similar, right? Like we're thinking of them. I think we're both thinking of them as trees to descend, right?
Yeah, and this one was actually great in this language because recursion works pretty well on a graph or a tree. Yeah,
and this syntax works really nicely because it's basically your if statements are in your method calls.
They're all in the pattern matching in the headers of those functions. Yeah, that's basically how functional programming works, but no one says it like that. It's a pretty good description. Rather than writing if statements, your function call. You can also have a when statement, which we'll probably see in some of my later answers, where you can do more complicated things.
Okay.
So you can run code as well.
Yeah. Okay.
Some code, not all code. I'm finding. What was the second bit?
So part 2 then was chaos, I think, for me. So I'm going to disclose in advance. I might struggle to explain my answer.
We're going to play the game. Does Jas understand KDB code from 3 weeks ago? Less than that, about a week and a half ago.
No, is the answer. So this one is orbital transfers. So you know where you are and where Santa is, and you've got to count.
I love a good picture.
Minimal number of transfers.
So the answer in this bolded bit is from you to Santa is 1, 2, 3, 4, 5, 6. 2, 3. 4, 5, 6. Is it? 6. Is the answer 6? Does it say? Minimum of 4.
Yeah. So you've got it's moving this line. So you go 1 to get to J, 1 to get to E, 1 to get to D, 1 to get to I. So it's 1, 2, 3, 4. Yeah. So it's that -2. You could argue.
Yeah.
And then you look like this. So then you've got to work out
what's the minimum?
How you're going to transfer from wherever you are in your input to that one. Would you like to go first?
Yeah, we could see.
Or would you want me to go first?
You can go first if you want.
Unfortunately, I've clicked my own answer, which is a disaster.
I think this is self-explanatory.
Yeah. Ugh.
So the first 2 lines are the same.
Yeah.
I'll let you take it from there.
Thanks, Rich. Nice handover. So I think what you'll notice, so this is the same as this, and I'm keeping track of the subtrees of each of the initial values. So I'm saying, so because I did the values of this map were all of the keys. I'm saying just give me a map. Give me all of the subtrees for each of the elements that I'm care about. So you see that right-hand bit and that left-hand bit are the same.
Yes.
And I've got an exclamation mark, which is the build a dictionary operator.
Right.
So I'm saying, for each unique element in my whole store, give me all of the child descents of that, and then keep them as a map.
So is the key? So the key will be so if you had ABC only, the keys would be ABC.
Yeah.
Yeah.
And then the values would be
the whole tree.
The tree down from A.
Yeah.
And then what I did is I said, what's the highest starting point where both San and U are in?
Oh, that's interesting.
So in this example here, my output would give me D.
Right.
So all of this I don't care about because I can never navigate above D because because it's a tree, they both have to be below that point.
Yes.
So E wouldn't work because San's not there, but D would.
So everything to the left of D would work.
And then D is the last one that would work, I should say.
Yes.
So D is the lowest one that I could still see both U and San.
Yeah.
And then things happen. Subtree root, subtree depth. Oh my god, I don't know.
These functions.
Yeah, these are all like result sets. I think.
Oh, you're assigning it.
Yeah, I think the way this is working is from here. Then I can count how deep San and U are away from this, and just count those 2 numbers.
Yes, and add them together.
Yeah.
-2 maybe, roughly.
Yeah, -2 because you take off like.
There's a -2.
Yeah, because it's the 6, right? So here it would be how deep is San from here? It's 1, 2, and it's 1, 2, 3, 4 to U. So it's 4 plus 2 minus 2.
Yeah,
and that gives you the 6. The complexity here is because of I'm not going to go into it, but it's because of the way I stored the output here to give me the easy count, then made it very hard to inspect.
Right.
How to get out the depths. So I had to I can't even remember what this does, but I had to flip the structure, which is what flip does. It literally translates it from one side to the other, and it's a bit of a mess. But it would give me how far away.
I think you've solved this in quite a different way from me, if I remember correctly.
Just in terms of how I'm explaining.
Yeah, you're not just even how. I think your technique's different.
Yeah, ignoring the
ignoring the coding bit. But I think it is. But let's see.
Let's have a look.
We'll find out.
This is still quite short though.
Yeah, I spent quite a lot of time tidying this one up. I think after I got the right answer, I think I spent another 10 minutes.
Yeah.
So shortest transfer
from to and your orbits.
Yeah.
Which you've parsed. So is that parse orbits the same as?
Yeah, I think it's not.
Oh, that's just that.
Not changed. Yeah. So.
Yeah. So you doesn't you use the result of the one from before.
No, because actually I felt that it was the same as you. It just wasn't actually really helpful.
Yeah.
Other than the parse bit.
I should have gone that way.
This is one of those ones where it doesn't really lead on. Other than the.
So you got shortest transfer here, and then it's calculate transfer lengths. From to
basically this function, if I was writing this today in Haskell terms, would probably be called shortest transfer _ helper, which I think is because I'm basically just having to add extra parameters for recursion.
Yeah,
but it's really just the shortest transfer. I mean,
so how did you? Well, that's the question then. How were you going to work out the transfer length? Are you actually going to go from one to the other, or did you do it the way I did, which is count from the highest subroot?
I did not. I don't think I did it the way that you said. I can't remember how I did it. We're going to find out, but I think I'm saying.
So calculate transfer length. So then, if that orbit is empty, then it's 0. Right. So this array is empty. So that's the easy case. That's the end case. But you're passing orbits twice.
Yes. because I think that's just for recursion purposes. I have a set of orbits which I'm making smaller as I traverse, and I have all the orbits just for reference.
Okay.
Because I can't remember why that is. I guess probably because I'm searching around.
So what's this one doing then?
So let's see if we can see.
Oh, I
so
see.
This is one of those when statements, which is basically like the pattern matching, but not. So it's a piece of code which basically says, like before we were saying, if it matches in the header.
Oh, here, yeah. So when this is true with this method, then do this thing.
And if it doesn't match, then it will drop through to another function definition.
That's interesting.
So this one is like when you're going from to an orbit, you have the length so far, and when from or to is equal to orbit, basically, is what that says. So,
but that's like two. That's almost like saying orbit's two elements, and you.
So an orbit might be A, comma B.
Okay, yeah. So
an orbit. I don't know why I said orbit, because that's not really an orbit. It's a moon. So orbit should say orbit could be A, and then it could be A. You're going from A to B. So if that's the case, then it's the length so far minus 1, apparently.
Okay. We haven't added one yet, so it might make more sense in this big one.
So that's another. That basically means that you're at the beginning of the end of a chain. So because either from or to. So if you're going from.
So you're minusing one there is like my -2 because you'll hit that twice.
Yes, you'll hit it twice. So it's exactly. And I think what it was I ran it and then I was like, I need to -1. And I didn't code it like that, but yeah.
So this is the big boy.
Yeah. So if you're going from, say, like A to B, if from is in orbit,
But is that just an atom? You could just do equals there, could you? Are they not both like atomic values? I read in as like it's like checking if an atom is in a list.
I'm surprised. I'm confused why that doesn't match the one above as well. But okay, I feel like
because you haven't got this when, right?
Yeah, but I feel like if it drops through to this one, then the top one would always catch it on line 12. But maybe I must be wrong because I can't imagine this works without it. Looking at it.
Well, no, but it's the other way around, right? So this orbit is 2 elements, and you're checking if the from piece is in that list of 2 elements, right? Whereas this is the other way around. It's saying from to as an object, and to from as an object is orbit one of those.
Oh, okay, yeah. So, that's the difference. So, so you need to in the top one you need to match both.
Yeah.
So, if from is A and B is and 2 is B, then orbit would need to be AB or BA.
Yeah.
So it's literally it's a one hop winner.
Yeah.
Yeah. Whereas this one's not like that. So this one is
just saying if from is either of them is basically what it's either of A or B in this one, right?
Yeah, it looks
sorry, in this.
Yeah. So if either exactly. If A or B is in there, so then you remove that orbit from the list.
Yeah.
And get the first one. So that's apparently the one you're currently orbiting.
Yeah.
Which kind of makes sense. This is not actually that easy to understand at all compared to the first part. And then
take that orbit out of all orbits, is it?
Yeah.
And then you've descended one, and then you need to calculate the length of everything else.
Yeah. So the top statement's like you're onto a winner, so add 1 and keep looking, but remove this one because we've already searched that one now. So keep and currently orbiting as well has changed. So you're not going from to. So say you've got a chain like A, B, C, and then you find B. Say you need to go from A to C, and the chain's A, B, C. You're at A, so this would all apply, and then it would say, A is currently orbiting B. So then you'd call it again with BC.
Yeah.
So you're sort of like what you're going from and to, or I think mainly from keeps changing. So you're from eventually we'll get to the one before Santa. So it's a bit confusing.
No, I'm just thinking because all your input is the input list, so you don't actually know. You're building the relationship, I guess, as you're adding this up, right?
Yeah.
Because you haven't got the state. I guess that's where it's different.
It's really different.
I had all of the layouts before.
Yeah, and I think you basically calculated the graph properly, and this doesn't do that at all, which is...
But you're sort of building the graph as you go, because you're saying, okay, I know how far I've gone.
Yes. Yeah, it's very recursive. So I think that line 18 makes sense. It's like you move on the from to the next one that you found, and then you remove the one that you found from the existing list and carry on traversing.
But this is then you're passing all of them in for reference.
For reference, yeah. And
but where do you ever modify this all orbits?
I don't. It's just always there for all reference. I don't know.
How do you... Oh, I see. Because at the starting point, you pass them both, don't you? Yeah. So you're taking from this one, you've got all of them for reference.
Yes.
And then eventually you'll be like, this is empty, i.e. I've been through the whole thing.
So
then I break out. Okay.
So then the line underneath, so you basically say, keep looking, and then you also say...
Are we here now? 21?
And now I'm 19 as well. So it's like keep...
Oh, yeah, so there's a bracket there. So you've done that, and then you're adding to it the tail of the orbit list.
Yeah, so which is the same as the line below, which is basically like, and just keep looking.
Yeah. So at this point, you're going to recurse from that one you've orbited all the way down, and then you've got to recurse on the other side of the tree, basically, the other branch.
Yeah, you just keep going.
Yeah, there's a lot of recursion, isn't there?
Yeah, and then that's just
the
like,
same
you didn't find one. Yeah.
Okay.
It's a bit weird. And to be honest, I feel like there's some luck in this algorithm because I think there is a bit. I think there are some, not luck, but I think there's some oddities about how it works that means that it works, which is like...
It'd be interesting to see how it, as it printed it out, I think it would be interesting to see how
I guess it just comes up with a number.
Yeah, so you could print, as you're adding one to length, you could be like, where was I and what was the length?
What's particularly strange about this is how it doesn't accidentally return a longer length. I actually, looking at it now, don't understand. And I think that's where yeah, I'm not sure.
Okay.
But yeah,
it's an interesting one. Yeah, no, it's interesting.
Yeah, I think it could be written better.
But I remember, like, on mine, the first bit I did quite easily. The second bit, because of the way I'd gone down, it just took me ages and ages. So I think, like, starting from scratch there was not a bad idea.
Yeah, even if you do end up with a recursive cluster.
Well, you didn't get like a stack error or a stack overflow, so...
No. Well, probably along the way I did, but not in the end. So next one is day 8.
Yeah. So again, we're ignoring all the Intcode ones. We might come back.
And then we're not going to do the 2 difficult ones because they're not fun.
So we'll stop at this one. This one was quite interesting.
Oh, this one was relatively easy, actually, as they go.
So this was, you have to parse some binary data as an image, and then what did you have to do? To make sure the image wasn't corrupted during transmission, which layer has the fewest of 0 digits? So it was a layering. So you had a pixel, you had an image, and then you had layers, and then you had to use the layer concept to make sure you wrote the right image, right, the right value.
Yeah.
So layer 1, it's like layers in Photoshop.
Yeah, basically it's like layers. So layer 1 there, the top left pixel is 1, then 1 to the right of that is 2, and then if you go down to layer 2, the top left pixel is 7, and it's like which layer has the fewest zeros. Yeah. Which is a weird. This is another one where I think the first question was almost
too easy.
It was almost a complete waste. It wasn't really anything to do with the second part.
Oh yeah, the visible pixel, is the second part. So even the first part was sort of very abstract. It's like, well,
which layer? So what is fewest zero? Yeah.
Well, and then what is the number of 1 digits multiplied by the number of 2 digits?
Yeah,
that layer,
which is a classic advent of code. We need you to generate a number to paste in. So we've come up with some random calculation at the end just to turn it back into a number. Yeah.
So this image is 3 by 2. So each layer is basically 6 pixels long, and then each width of that is 3. So I guess you're going to use that in your solution. What day was it? 8.
See. Well, it's longer than I'd have thought, actually.
So calculate checksum, input 25.6, and input calculate checksum is here.
Yeah.
So your layers.
So image layers.
All the layers, which is image layers, which is here. So you parse the image,
which splits it by empty. Rejects any empty. That just because when you split by empty, you get an extra element, which is just empty string at the beginning and the end. So it just gets rid of that. So that's a bit relevant. And then parses them as integers. So basically, you get everything as integers.
Yeah,
and that's it.
And then you got this nice chunk every,
which is a beautiful function. Which just if you have an array like 1, 2, 3, 4, and you chunk every 2, you'll get an array. You'll get an array which has an array with 1, 2, and then another array with 3, 4.
Yeah.
So you chunk by the width, you chunk by the right, and then you end up with an array of arrays for each layer, basically.
Yeah.
And then what's next?
Here, layers with least zeros. So sort by, count occurrences in layer.
Of 0, yeah.
So flatten it and count.
Yeah.
What's this thing? The digit you're looking for.
Yeah.
Yeah.
And then...
So where the digit matches, count that, sort it by that, and then it's the first one.
That's pretty easy.
And then, find the first layer and the second layer.
Yeah.
Count the number of ones and times them
Count
together.
occurrences of layer. Oh, okay. Count. Oh, I used that function again.
Yeah, it was nice bit of reuse.
That's glorious.
Like the 0, the 1, and
I love the
two.
way I'm surprised, even though I wrote this a week ago. So yeah, that was pretty straightforward actually, despite being a bit of code.
So let's have a look. I do feel like this one was okay. Yeah, I basically did it exactly the same way. So cut is like your chunk. So I basically cut it by the total image size, and then each of those I've cut by the width, so it gives me an array of arrays.
Yeah.
And then an awkward way of having to count the zeros. So what I didn't do is parse them into integers. I kept them as characters.
Yeah.
So then because they're then strings, to then look into the character, I have to treat the string as a list. So that's what I have to look into it to do, equals into each array and then into each string.
Yeah.
Count them up. What's the smallest one? And then the same thing, give me the count of where they're 1, where they're 2 in that layer.
Yeah.
That's it.
And then times them
together.
Very nice. And then the second part was... So for each position, say 0, 0, or the top left, find the lowest number wins. Is that right? Given an image, the lowest number wins?
No, the first non-transparent one wins.
Yes. What's non-transparent?
So 0 and 1 is 0 is black, 1 is white, 2 is transparent.
So the first non-transparent. So if you going from layer 1, 2, 3, 4, so going that way. If you find a 0 or 1, you keep it. If it's a 2, you keep on going down.
Yeah, exactly. So in this example here, the top left pixel, it's 0, 1, 2, 0. The top left pixel is black because it goes through the 0 and then hits 1. Yeah. And then after that, it's irrelevant.
Yeah.
And then, so it looks like this if you process it based on these rules.
And then the way this one works, which is kind of cool, is you print out the image that results, and the image that results has letters. You can see your answer there or my answer, LH, CPH.
Yeah, which was quite nice. These ones feel quite nice when you solve them.
Yeah, it's cool. It's really cool. Mine printed out in a way that was completely illegible, and I spent about 2 minutes writing it down with a pen and paper because it was really hard to read, even though it printed correctly.
You'll see in mine how I made it, trying to make it easier to read. So print image.
Image layers, which I feel... Did we have that before?
I think that sounds like a familiar one. Yeah.
Yeah, chunk every. Okay, so that's the same.
And then you've got your merge layers, which is the new bit.
Yeah.
So you've got... here are layers width and height.
This is a bit mucky.
And then you're going to...
The triple nested loop for the win. So for each position, so 0, 0, 0, 1, 0, 2, all the way up to height, and then for each width. So you've got your width and your height, so that will start at 0, 0. Yeah. And then you find the layer. Yeah, you find... Oh, that's interesting. I'm going to have to confuse myself.
So you've
merge layers. So that's misleading now. So it will get you...
It'll get you the right value based on the depth, won't it?
It will get you... So for 0, 0, it will get you the... In the first position, you'll end up with 0, 0. You'll end up with all the 0, 0s.
For that layer?
For that
pixel, all the layers?
Yes. Yeah, so I basically rearranged it completely. Yes. Because to me, that's actually... Then you can start processing them based on the logic. Because that's the main problem.
You want the layers by pixel rather than the... Whichever way it is, you flipped it on its head.
I flipped it. So before you had each of the layers one at a time. Yeah. Now I have each pixel and I have the value for all of the layers for that pixel.
Yeah, that makes sense. So that's the same
and
way.
And
then calculate image output is this one.
So
for each row and each pixel, calculate which pixel, right?
Yeah. And that's here. If you find...
0 index and 1 index.
Yeah, so so you find the 0 so if, say for example, in the first example we looked at, it was 0, 1, 2 something.
Yeah.
So you find the 0 index, which would be 0, the 1 index is 1, and then 0 is, you found the 0, 1 first, so it will just return 0. So if you look at line 31, it says what's the index, which layer is the 0 in, which layer is the 1 in, and if the 0 is before the 1, then return 0, and if you found the 1 first, then return 1.
Because you can just ignore the 2s altogether.
Yeah, the 2s are irrelevant. It's literally which one did you find first.
Yeah, and then you got to print it. which is this. Yeah.
Join
them out and then new line it between the...
and that printed something which was completely illegible. But I studied it and got the right answer. But that one was pretty straightforward. I feel
like that's very similar, but let's have a look.
Well, yours is very short.
Yeah, this one just happened to be quite nice. So yeah, I did the same thing as before. I got to cut the image up.
Yeah, that's completely the same, isn't it? Yeah.
And then I've basically done the same thing you have done. As you see here, it's image by pixel. So I've cast them all into a H, which is a short integer, because it's the letter before I.
Yeah, obviously.
And then, I flipped it. So now I have each pixel by the depth.
Yeah.
By the layers. And then, what have I done here? Yeah, and then I'm doing the same thing as you. Which is the first element of each of those where it's not a 2?
Yeah.
And then look that up. So what I've not done, so I haven't done anything with 0 and 1 here. So what I'm saying is, which layer has the first 0 or 1, and then tell me if it's a 0 or a 1.
Yeah.
So I'm saying it'll tell me, it's the first layer. This will tell me, and then I've got to go back into the image by pixel.
Yeah.
And say what was at the first layer, and it'll be
that's like looking
0
it up.
or 1.
Yeah, that could be like 2 lines.
Yeah, it probably could have also been more like yours, where you could have just said, well, which is what's the first not 2? Which is the first non 1 or 2, and just tell me that.
Yeah.
But anyway, and then I've got to cut it back because the way I flip this, I've now got to then regenerate the width to get the right pixels, and then all of the zeros I replaced with a space,
which is the smart way,
and then printed it out.
Yeah, because then you can read it.
Yeah.
Cool.
So that was the way I did that. Yeah. So this .q.s is like it's like to show it, but it gives you a string so you can post-process it, and this is like a string search and replace.
I must say, before we leave KDB, I can read most programming languages, even if I don't know them quite well, and this language
is the
least understandable language I've ever encountered by some margin.
Yeah.
I would say. Maybe there are some others that are quite bad, regexes and awk and stuff, but yeah.
I think, like I said, I said before, I definitely haven't written this in a nice way.
Right.
Because at the end of the day, I'm just trying to solve it quickly. So there would be nicer ways to solve it. Like, I was talking to some guys at work, and this operator that you're nesting it.
Yeah.
I think we decided that if you saw that in any real code, you'd be highly doubtful that it's the right thing to do.
Right.
Because it's just so weird to see and really weird what you're trying to do.
Yeah.
So I think a lot of that is because the problems are quite they're quite I don't know what the right word is, because they're not really what KDB's for. We're then sort of abusing the language a little bit to solve them.
Yeah, there is an element. Elixir is quite well suited to this, whereas KDB, it's not its bread and butter.
Yeah, so like I say, if you saw code like this in an actual KDB application, I would be sort of like, what is going on? Because
there are a lot of places where you've been going through the code where you can tell it's awkward for the language.
Yeah. And I think, this sort of stuff is quite awkward because of the way I'm having to do these lookups. There are some things which are quite nice. So like the fact that I can look up all of my image layers in one go with this, like from what this lookup.
Yeah.
Nice. This, not nice. This, and the cut is quite nice, but then you got this lookup up here, which is just it's just a bit crap.
Yeah.
And I think if you were doing it properly, you'd probably make more of an effort to translate it into a structure that makes more sense for KDB, so like dictionaries and tables.
Yes.
But again, for convenience and speed, it's like, how can we get the information out as quickly as possible?
Yeah, it's kind of like if you were to try and solve these with SQL, it's definitely going to be possible, but it's not what it's designed for. I don't think this is as bad as that, because this is more quite a lot. You seem to have quite a lot of things that, I don't know SQL super well, but
yeah, this is a fully fledged programming language. It's just that it was written with a particular slant, so I wouldn't call it a general purpose programming language at all, because it really isn't. It really is time series data. Yeah. How do we access that data really efficiently and quickly, and do aggregations and data analysis on that?
It just so happens to have enough features to also complete this, but it's not its primary thing. Yeah. It probably is. It is probably technically a general purpose, but it just wasn't designed.
So what I would say is, although we're not going to do it, if you look at the Intcode solutions, I think I would hope you'd find them a lot more readable, because basically I've just got a big while loop. and then you'll see I think it looks more like a standard code. So you've got like your
Yeah.
operations,
Yeah.
and then your
That is
jump.
more
So
understandable.
so there's, it's easy to see, but it's not as easy to see when we're just running through it. But it's a lot easier to read because it's more like how I would go back to writing KDB. So like you see, like I'm modifying the index in a pretty traditional way.
Yeah.
And there's a few oddities in here, but it's more how I would like to read KDB.
Yeah.
Because it just looks more like actual programming language.
Ironically, that looks nothing like my Intcode solutions because I can't modify things.
Yeah, so that
mine's
must be
mental.
awful.
Yeah.
Anyway, we're not going to go through that. Okay.
Cool.